Alright, here we're going to actually find the linearization of a function at a point. And the first thing I usually like to do is just jot down the general structure of it. So L of x equals f of a plus f prime of a times x minus a. And I recommend remembering this here, because later when we do Taylor polynomials, you'll want to see that this can be generalized to even higher degree polynomials, not just lines. But our a is 0, so that means we want L of x to be f of 0 plus f prime of 0 times x minus 0. Now f of 0 is just natural log of 0 plus 1, so it's natural log of 1, which is 0. So that's just a 0 in this case. F prime of 0 would be the derivative at 0, so we've got to find the derivative first. So the derivative of a natural log of x plus 1 would be 1 over x plus 1. And then if I plug in 0, I get 1 over 1. So I get 1, 1x. So the linearization is x. And so what we basically saw, or what we're seeing, is that if you take the natural log of x plus 1, that graph looks like this. It's a natural log graph shifted to the left 1. So it has a vertical asymptote here at -1. And it's behaving like this. And what we just found was that, well, actually, that sketch isn't accurate enough, because the natural log when we plugged in 0, we got 0, so it needs to go through the origin. So that's important, actually. So it looks like that. And what we just found was the linearization L of x equals x is the tangent line at x equals 0, and that is what we would want to use if we wanted to approximate the natural log of x plus 1 for values close to 0. And so, in terms of approximation, that's what this bottom question is asking. It says how accurate is the approximation L of a plus 0.1 when you compare it to f of a plus 0.01? Well, our a is 0, so let's just get these values. Using the linearization, L of a plus 0.01, in this case, is L of 0 plus 0.01. So it's just L of 0.01. And if you just plug that into the linearization, it's just 0.01. Or 0.1, keep saying 0.01. On the other hand, f of a plus 0.1 is the same as f of 0.1. And here you'd have to plug this in to the natural log function there. So it would be ln of 0.1 plus 1, so it's ln of 1.1, which is about equal to, if you put that in your calculator, 0.09531. And so how accurate is the approximation? Well, let's just find what's called the approximation error. It's the best way to answer that question. So I always view this as the absolute value of the actual value minus our estimate. Now our actual value was 0.09531, and our estimate was 0.1. And if you do that subtraction out, you get 0.09531 minus 0.1 in absolute value. You get about 0.00469. So you could say the error is, 0.004 is less than, that's less than 100th, right? So you could say this is less than 100th. So we're within 100th of the true value of the function if we use the linearization to approximate the function at a equals, or at the x value 0.1. So that's not bad. That's actually a really good approximation. If you're ever doing something and you need to be within 100th, then you can just use the linearization as opposed to the actual function itself. You can use linearizations to approximate things like square roots. And the way you would do that is you would actually need to construct a linearization to a function, and the function you'll probably want to use is the square root of x function. So we're going to let our f of x be the square root of x function. And we're going to just make a tangent line, and we're going to choose a value whose square root we know to be the center of our approximation. And then we're going to plug in 117 into our function and see how good we do. So before we get into that, let's just note what the actual value of the square root of 117 is. So if you put that in your calculator, you get about 10.8167. Alright, so that's whatever our linearization does, we're hoping it'll be pretty close to that. Alright, so let's put in a visual here too. There's my square root of x function. Now, I know, I mean, in order for this to work, I want to find a square root, or I'm sorry, I want to find a square which is close to 117, but whose value I know. And I would think that 121 is probably the closest one that you can find. So 121, we know the square root of that is 11. I'm going to construct my tangent line to be there. And so then what I'm going to do is I'm going to make my tangent line, and then I'm going to plug in 117 into it and see how good a job I do. Alright, so, or how good a job it does. So we know that the general structure of the linearization is this. Now the A I'm using in this case is 121 because we know that square root exactly. And one thing I'm going to need to know is I'm going to need to know the derivative of root x in order to find that slope there. So I'm going to write this as x to the 1/2, and then when you take its derivative, you get 1/2 x to the negative 1/2, which is 1 over 2 square root of x. And so that means that f of 121, which is the square root of 121, is 11, and f prime of 121 is 1 over 2 square root of 121, which is 1 over 2 times 11, which is 1 over 22. So now I can finish up my linearization. F of a is 11. F prime of a would be 1 over 22, and my a is 121. So there's my linearization. Now I actually got to use it now. I got to use it to approximate the square root of 117. So I'm just going to plug in 117, and we're going to hope, or we're going to compare its value to the actual square root of 117 that we found above. So let's do that. L of 117 would be 11 plus 1 over 22, 117 minus 121. And that ends up being 11 plus 1 over 22 times a negative 4. So it's 11 minus 4 over 22, which is 10 and 18/22. And 18/22 is about, or its decimal approximation is 0.8181, and that repeats. So we'll just write it as 10.81 repeating, and then that wouldn't be about equal to, it would be actually equal to. Alright, and so that's pretty, if you go compare it to the actual square root, you can see it did a really good job. And we weren't even that, we weren't that close to 117 isn't that close to 121, but our linearization did a pretty good job of approximating it anyway. So if we wanted to quantify how good the approximation was, we'll do the approximation error here. So that I call the actual minus the estimate, which would be the absolute value of 10.8167 minus, we'll use 10.8182, and that's about equal to 0.0015. So that's less than a tenth. So we're within a tenth of the true value by using the linearization.